Hey guys, welcome to the next video on SN1, SN2, E1, E2 stuff. So we're going to just quickly summarize what we've gone over in the last few videos, and then we're just going to mainly go through practice questions, okay? So I wrote out some stuff here for you guys that kind of summarizes what we've talked about. Now, I know I've told you guys in the past, don't use charts, all right? I should have been a little bit more, I should have clarified a little bit better. A good chart to have on your index card is maybe something about like the strong bases, the weak bases, the good nucleophiles, and the bad nucleophiles. And I wrote this here. You may have seen something very similar. I just pretty much took it about what's floating around. I think that this is probably the best one. So I wrote here the strong bases and the weak base, the good nucleophiles and the bad nucleophiles, and also leaving groups, right? Now again, to use the chart on a test or on your index card is fine, but you need to understand the process of it in terms of you need to understand the chemistry behind it. All right, mindlessly using a chart is not going to help you. Like I said before, there's going to be a question on the test that is going to test whether or not you're mindlessly using a chart or whether you actually know what you're still talking about, okay? And sorry if there's some background noise. I'm filming this right outside the chemistry library, so you may hear people coming in and out. And so yeah, so again, be careful. I have here leaving groups, the nucleophiles and the solvents and the different types of solvents, right? So you should still understand how these work in terms of how they apply to SN1, SN2, E1, E2 stuff. But you can have it on your card in case, obviously, if you forget, you don't want to be in a situation where you forget the reasoning behind something, and that's the reason you get it wrong. So of course, as a contingency, you can put on your card. And over here, I wrote a summary of how we determine SN1, SN2, E1, E2. Now this of all the stuff that I wrote here, this is the thing that you need to be the most careful about. All right. The other stuff you can have in your index card, and usually you will get the question right. But this right here, where I wrote "be careful," is what you need to watch out for. There are a bunch of examples where this summary right here will not work. All right, and you need to watch out. So again, chemistry exists, guys. All right, you have to think logically, right? And you have to use what you know. So relying on these charts, at least specifically on this one, can really mess you up. Okay, so like I said, mindlessly using a chart is not a good thing. There are going to be questions where you can use one of these charts and you can go through it pretty quickly and get it right. But there will be questions that they will specifically put weeding out people who are doing this. All right, so please be super, super careful. All right, like I said, take it with a grain of salt. And also, yeah, this is the best one that I could find. But again, use what you know. Don't always rely on a chart. All right, and so we're going to go through some practice problems, and I will show you guys examples where using a chart, exactly this one or another one, will 100% get you the question wrong. All right, because people would mindlessly use it instead of thinking the problem through first. Your default mode should not be looking at the chart. You should always be thinking about the question. All right, so I'm going to just write out a practice problem for us. Actually. And I did post a practice problem set for you guys. And some of the questions I'm going to be pulling for these videos will be from the problem set. That way I can go through them live with you guys. Well, not live, but you know what I mean. You can hear me go through it because I usually do post a key for these things, but I know some people want explanations. Then I do try to explain them, but when I post the key, it's a little bit hard to go through a full-blown explanation written. All right. So this question is going to ask us to draw the major products or product and to include stereochemistry where appropriate. Okay. So always the first thing we want to look at is the substitution pattern, right? And what I mean by substitution pattern is is our leaving group primary, secondary, tertiary, all right? So if we look at the carbon with the Br, it's bound to two other carbons, so it's a secondary one. So right off the bat, this is going to be the most complicated in terms of right here. You can see over here, right? We have to look at a bunch of different things to determine if it's secondary. And so we can't really eliminate anything in terms of SN1, SN2, E1, E2 stuff, right? Because a secondary carbocation is somewhat stable, right? So that means we can't rule out SN1 and E1. We can rule out SN2 just because SN2 does work on a secondary. And we can't rule out E2 yet because it can work on primary, secondary, or tertiary. So we're kind of stuck. So when you can't use the leaving group itself, or the substitution of the leaving group, we look at the nucleophile or the base that we're reacting with. So in this case, it's KCN, all right? So you've seen CN in terms of CN minus, right? This is what they'll do in a test is they'll write it as a salt, which really means that this is a K plus and this is a CN minus, and all we do is ignore the K, all right? So don't get tripped up in terms of that. You'll see either K plus or Na like sodium, right? So all you got to do is just cross out the first that first metal. So we're reacting with CN minus. Now CN minus is a good nucleophile but a weak base. And if you're confused at what CN minus looks like, it's a carbon with a negative charge triple bonded to a nitrogen. So that's CN minus. So it's a good nucleophile, but it's a bad base. All right. So we know that SN2, right? The more sterics we have, the more sterically hindered our leaving group is, the harder it's going to get. So secondary is stretching the limit of an SN2. All right. The only way an SN2 will work on a secondary leaving group is if we have a good nucleophile but a bad base. If we had a good nucleophile and a good base, then the base character will predominate and we'd end up getting an E2. Okay, so we have a good nucleophile and a bad base, right? So we're going to get an SN2 here. So what's going to happen is, remember, SN2 happens in one step. This carbon is going to attack and do a backside attack coming in from the back and kick our leaving group out. So we're going to get, remember, in an SN2 we invert the stereochemistry because the nucleophile is coming in from the back. So we're going to get now a dash CN, and this dash methyl stays like that because, well, we didn't affect it. And if you're wondering how we would have written this out using the full structure of CN, it would have looked like this. All right, that triple bond, and we get that dash methyl again. So that would have been our answer. All right, so you can see we have to invert the stereochemistry of an SN2. All right, and you can see they gave us a solvent, DMF, right? But we didn't really use that. Why? Okay. So here's the thing. The solvent is overemphasized a lot. Most of the time you can actually figure the question out without even using the solvent. The solvent just kind of pushes you in one direction. So what they will do oftentimes is they'll give you two leaving groups on a molecule, but they will give you a solvent. And you'll be in a situation where you're deciding between like SN1 or SN2, right? Yet the solvent can help you determine which of the leaving groups undergoes which one, or if one doesn't even change at all. All right, and again, I'll show you some examples like that later on. But yeah, the solvent a lot of times is a little bit overemphasized. So that's how we would have done that question. Let's go on to another one. So let's take this question right here. So they gave us this structure, reacting with NaCN over DMF. All right. And so what exactly are we going to do here? Well, let's look at our first substitution pattern of the leaving group, right? They gave us a primary leaving group because that carbon with the Br is only bound to one other carbon, right? We have a good leaving group, it's a Br. So using what we know of SN1, S2, E1, E2 stuff, we can eliminate carbocation reactions, right? If we were to have a carbocation, the first arrow would look like this, and then we'd get that carbocation. That's a primary carbocation, and that is not stable to form. Now you may be thinking, but wait, we can shift it to using a hydrogen from here and get a secondary carbocation, right? But that primary carbocation still has to form, and the formation of it is already unstable. So in terms of E1, E2, it's not going to, E1 and SN1, it's not going to happen. So now we're just down to SN2 and E2. Now, SN2 is good when we have an unhindered leaving group. So that means methyl is the best, primary is the second best, secondary is stretching it but can still happen, tertiary just won't happen. So primary, good for SN2, but we can still get an E2. The case where we can get an E2 is if we're reacting it with a bulky base. Okay, something, because if our attacking molecule is bulky, well then it can't perform an SN2 because it's too big, right? And so it'll go E2. So what are we reacting it with? Here we have NaCN. Remember, very similar to what I set up here with the K. This is just going to be Na plus, Cn minus. Disregard this Na plus. So all we have is that we need to look at Cn minus. Well, this is a good nucleophile and a bad base, right? So good nucleophiles, right? I mean, it would be better for an SN2, and the fact that it's a bad base isn't going to help us do an E2, right? E2 requires a good base usually. So this is going to be another SN2, and so the arrow, let's just erase that one, is going to look like this, kicking out the Br. Remember this methyl right here, we never touched it, so it stays wedged. And then we write Cn. Okay? Now you may be wondering, is there stereochemistry here, right? We know that SN2 inverse stereochemistry, so are we going to do that here? Well, this carbon right here in blue and the one on and the same thing in red on the left, it's not chiral. It has two hydrogens, so there is no there is no point in specifying wedges or dashes, and also they wrote the leaving group as planar in the first place, right? The opposite of planar, well, it's just going to be another planar. Okay, so this would have been our answer, just a CN coming off that carbon. And again, you see, I didn't even touch the solvent. Okay, a lot of times, like I said, solvent is a little bit overemphasized, so don't worry about that too much. So now let's do another question. This one's going to be a little bit different. So we have this leaving group, this product, and this is the reaction OET over ETOH. All right. So what they're asking us is to find the initial reactant, and they gave us this formula, CnH17Br. All right, so that can help you. So what we need to do is we need to find the reactant, right, given this product. So the first thing we should know OET, right? The ET stands for ethyl, and the O with a minus charge. So this just really looks like this. And ETOH is this right here. All right. So that's all those things are, OET and ETOH. You could have seen OME, which is just the same exact thing written over here, but with a methyl. All right. So that's the terminology. So we need to find the original reactant. And so you can see that our product has a double bond right here. And our initial reactant, we can see that it has a Br. Okay, so we had a Br, which was a good leaving group, and we ended with a double bond. So we should now be thinking that we have an elimination reaction. But is it E1 or is it E2, right? Well, we have a strong base, right? So a strong base means that we're going to go E2, okay? So there's no carbocation intermediate in this reaction. And so we now need to get the reactant. So now you could essentially kind of help yourself out here. You should know that the majority of the structure should remain very, very similar, right? Because well, it tells you the same amount of carbons. The only difference is really the Br, and we didn't have a double bond. But, all right, and so we have something that's probably going to look somewhat similar to this. Okay? Now, the thing that's the key to this problem is knowing that in E2 reaction, right, that in E2, the leaving group and the hydrogen that's going to be taken to form the double bond must always be opposite stereochemistry. That means, so we know that we have a Br leaving group, so that means if our Br, wherever it was wedged, the hydrogen that's going to have been taken to form the double bond should be dashed. If we had a dashed Br, the hydrogen will be wedged. Okay, that must always happen. So let's look at our double bond right here. So we have this double bond next to, and it's connected to this group right over here, and this carbon right over there that's connected to like the rest of this ring over there. Okay, so we have to think about how we're placing this Br. So let's just say I put it here. Right, you see I'm not specifying any stereochemistry. So if we put this here, we know that it could form a double bond here, or it could have formed it here with equal substitution, right? Okay, so that means that's one possibility, right? If I formed it there, it could have formed, again, either there or there. That's another. But like, let's look at the first case. I'm going to put the Br there. Now what I'm going to do is I'm going to give it stereochemistry. So let's say put a wedge. Okay, so I put a wedged Br right there. Okay, are we going to get what is our E2 product going to look like if we try to do it this way? Well, we have to look at both possibilities of the double bond. We can put we know that the hydrogen here will be dashed because the methyl is wedged, right? So in this case, if I make our Br wedged, that hydrogen is dashed on the left. So it can definitely do an E2 reaction and give us a double bond here. But that's not our product. And you can also see that this methyl right here stays wedged. The double bond doesn't form right there. So what you want to do is avoid the formation of the double bond there. But if you make the Br wedged, we can't. That could have happened, right? So what we now need to think of is assigning stereochemistry to this group, or specifically that bond. All right. So we want to avoid the double bond forming on the left. So first, let's change the Br, stereochemistry. We know that that's supposed to be dashed. Right? Okay. So making the Br dashed is definitely going to make sure that we can't get a double bond forming there, because the Br and the H are now the same. Now the same stereochemistry. Now we again need to form the double bond right there. Correct? So we have to form the double bond right over here. And again, E2, the hydrogen must be opposite. So now what I'm going to do is change the stereochemistry of that group. If we make that dashed, the hydrogen there will be wedged. Now this is perfectly set up for an E2, in which our good base is going to grab that H. This bond is going to come down, kick the Br out. So we're now going to get this double bond here. The wedge stays the same, right? And because we formed a double bond, all the substituents on the carbons of the double bond will be planar. So we now get this. So that is our product. Now, what about if I put the Br not where I just put it there, but the other possibility that we talked about, right? So we have this now, right? Can it form the double bond there? Now, this may be the other tempting answer, putting the Br there. But here's the problem with that. If you look at this carbon and this carbon, they're equally substituted, right? And you may be thinking, sure, they're equally substituted, But what about just changing the stereochemistry of the hydrogens so that it'll always form to that carbon? Well, each of these have two hydrogens on them, which means one will always be wedged, one will always be dashed, and the same thing here, because it already has two other planar bonds. So in essence, it's not going to help us by just putting the Br there, just because it could have formed on either side, and the one will be equally substituted, so it could either form there, or it could form right there. So putting the Br there will not help you. All right, so you wanted to put the Br right there. Okay, so that's how we would have done that problem. And so those are just a couple of practice problems for you guys. I will go actually through one more question. So let's see. I have this. And again, sorry for all the noise in the back. Okay. So it's going to ask us to draw the structures of the major product of the following reaction, right? And so, yeah, so again, just figuring out what the product of this reaction is. Okay? So, again, first thing we always want to look at is the substitution of our, the substitution pattern as if in our leaving group in terms of primary, secondary, tertiary, all that good stuff. Okay? So that's the first thing we want to look at. And so if we look at this, we can see that it's going to be tertiary, right? Our leaving group is connected to a carbon with 3 other carbons, right? So this is the carbon we're talking about. 1, 2, 3. All right, so that's tertiary. So can we eliminate any of our reactions right off the bat? Well, in terms of the carbocation reactions, we have SN1 and E1, right? They're going to form if our carbocation that forms can be stable. So let's draw an arrow showing how that rate would proceed. We get something that looks like this. That's a tertiary carbocation. Now, notice that the stereochemistry is gone. All right, this is a very important thing to understand. This carbon originally is sp3. It's tetrahedral, so it can have wedges and dashes. It'll have 2 planar bonds and 1 wedge and 1 dash. This carbon is now sp2. sp2 is planar, all right? Always watch out for that, and please make sure you understand that, okay? So carbocations lose the stereochem. So we have a tertiary carbocation, which is pretty stable, so we can't rule out SN1 or E1. We can rule out SN2, right? Remember, SN2 does not like bulky substrates. This is a tertiary carbon. So having some nucleophile, whatever it is, and you get through all this sort of stuff to be able to hit that carbon, right, is going to make it much harder, right? Doesn't like that. So we can rule out SN2. So now we only have 3 reactions left. Now we have to look at our nucleophile and our base. You can see it's CH3OH, right? That's just a methyl, right? Yeah, this. So is this a good nucleophile? Is this a bad nucleophile? Right? This is a good base. It's a bad base. Well, it doesn't have a charge, right? That's usually the thing that can help us figure this stuff out. This does not have a charge, so it's not going to be a good nucleophile. It's also not going to be a good base, right? For the very same reason, right? So this isn't going to be a good nucleophile or a good base. It's going to be weak for both. So what is this going to push us towards, right? So this is going to push us a little bit more towards the SN1 or E1 reactions. Again, how do we decide which one? Well, in general, E1 is very rare, right? Usually, most of the time you'll see it reacting with an alcohol and H2SO4 over heat. Now, I'm not saying that's the only case. I'm saying that's the one that happens the most often. But also, I said that SN1 and E1, the way we differentiate them is mainly based on if there's heat present. 25 degrees Celsius is room temperature, so this isn't a reaction where we would consider this as getting heat input. So this is not, so we can essentially write no heat. Okay? So this is going to be an SN1 reaction. So first arrow for an SN1 is the leaving group must leave. So we're going to get the carbocation. Now, always, 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 when you have a carbocation, look for shifts every time. Okay? It can happen. You always must look for them. Now, this is a tertiary carbon. That's a secondary. So it would definitely not shift over there because it's going to be going from more stable to unstable. Or at least not unstable, but less stable. That's a tertiary carbon, but that's the same as the one that we already have our carbocation on. So it's not going to shift there either. It'll only shift it if it can be more stable. So that's where our carbocation is. And now we can do our SN2. So this, our nucleophile, right? Actually, I'll write it like this, is going to attack our carbocation. Now, the key thing to watch out for on carbocations, remember I said that they're planar, right? So they're flat. So this nucleophile can attack from either the front or the back. No one can really tell which one it'll be. So it can attack front or it can attack the back. So we're going to get two possibilities. So I'll draw the one in red. Right? So if it came in from the front, you can say it's going to be wedged. Now I just assigned the wedge to front. I mean, it's up to you. The key thing is that you know that there can be two products. And the methyl and the dashed methyl over there. And remember, this oxygen has a plus charge now. And the other possibility, I should have wrote back. The other possibility is now this is going to be dashed. Again, plus charge. And the methyl will be wedged. Now the next step is always the deprotonation, right? We always have to deprotonate that H because we're not going to leave this with a plus charge. Now you don't have to really show what takes the hydrogen itself, but it's more times, most of the time it's just going to be the solvent again, so another one of these H3COH groups. You can now just grab this out, the H, and this bond goes here. Or you could just not show this at all, but you should show the arrow showing the oxygen-hydrogen bond breaking, because that's a key arrow. Okay, and so do the same for here. And so our answer is going to be two products. Draw that better. And a dashed methyl plus the other one we had. So we have, this is dashed O3C wedge methyl. Right? These are not the same. Right? We could have assigned R and S to see that these are definitely opposite. They're enantiomers. Right? So we get a mixture here. So remember, that's a very important thing to watch out for. That happens because we have a carbocation, and it's in an SN1. All right. Now in an E1 we would have gotten a double bond forming, so we wouldn't have gotten enantiomers, right? So yeah, always watch out for that in terms of SN1 stuff. Okay. And so this answer, the answer to this question would have required both products in order to get full credit, not one. You need to show both. All right. This wasn't a multiple choice either. It was a written question. Okay. So that's how we do these questions. In the next one, in the next video, I'm going to show you examples of where these charts do not work. All right. Because I want to get you guys to understand that while using the chart is okay, you have to be careful because relying on the chart and not understanding the reasoning behind it is what can screw you up. All right. And so I will see you guys in the next video. If something here doesn't make sense, please feel free to email me, go to the CLC for office hours, or if you're watching this on YouTube, comment so that I can answer it and other people may also see the answer. All right. And I hope this helps you guys out.